AI RAN model performance testing using a neuromorphic receiver as the device under test. This demonstration is part of the AI RAN Alliance Working Group 1, AI for RAN. Artificial neural networks offer high accuracy and adaptability, but are energy intensive, as their neurons compute weighted sums of continuous inputs and apply nonlinear activation functions. On the other hand, spiking neural networks are event-driven, energy efficient, and biologically inspired. SNN neurons integrate incoming spikes over time and emit discrete spikes when membrane potential reaches a threshold. ANN-based neural receivers provide significant performance improvement, but their high energy consumption limits practical user equipment deployment. Neuromorphic receivers use a single spiking neural network for channel estimation, equalization, and symbol demapping, reducing energy use with minimal performance loss through spike-based computation. Neuromorphic receivers, shown in green, achieve comparable decoding performance to neural receivers, shown in red, with modest degradation while reducing energy consumption by approximately 7 to 9 times. The evaluation framework incorporates white box and black box AI model testing. White box testing leverages full model architecture and training knowledge to assess robustness, generalizability, and interpretability under diverse channel conditions. Consider a neuromorphic receiver trained and validated on 100 parameter settings, focusing on carrier frequency, channel model, and mobility. The table shows all possible values per parameter. Known training scenarios appear as green circles. In distribution testing measures performance on training scenarios, the green circles, while out of distribution testing evaluates robustness on all the other scenarios. Black box testing addresses practical deployment where the model internals are unavailable. Vendors provide only model IDs without training data, specifications, or performance guarantees. Using the same parameter space but with unknown model and training information, testing would require exhaustive parameter coverage as the 3GPP parameter combinations grow exponentially. We address this through an AI-based generalizability testing policy. As mentioned earlier, testing AI-based neuromorphic receivers across tens of thousands of 3GPP parameters configurations is impractical using exhaustive methods, while random selection often misses critical edge cases. We propose a 4-step approach for black box AI model generalizability and lifecycle management monitoring testing. Step 1 is test case generation. Here, we generate comprehensive 3GPP compliant test cases by enumerating all valid combinations of system, channel, antenna, and mobility parameters, including multiple stochastic channel realizations per configuration. Step 2 is intelligent test selection. Here we apply an AI-driven selection model to identify a compact representative subset, preserving parameter coverage, reducing redundancy, and prioritizing stress scenarios likely to expose performance weaknesses. Step 3 is execution and KPI extraction. Here, we execute selected test cases on the VIAVI 6G testbed to obtain ground truth communication and energy-efficient KPIs under realistic operating conditions. Step 4 is performance prediction, that train a performance predictor model using observed results to estimate probabilistic KPIs and associated uncertainty across untested configurations, enabling scalable and cost-efficient validation of black box AI receivers. This solution requires no proprietary information, guarantees performance assessment across the complete 3GPP parameter space, and reduces testing time by orders of magnitude. At MWC 26, we will demonstrate this live on the VIAVI 6G testbed with an interactive GUI with video backup prepared. The VIAVI 6G test platform integrates hardware, software, automation, and infrastructure supporting 6G technologies. This shows our MWC GUI layout for AI RAN model performance testing, using the neuromorphic receiver as the device under test. This demonstration considers a downlink scenario where the UI uses a neuromorphic receiver to decode 5G NR PDSCH. First, functional testing evaluates decoding performance with communication KPIs, blur, and throughput. Next, generalizability and monitoring testing assesses AI robustness via black box testing, using generalizability as the AI-centric KPI. This approach requires no model or training information. Finally, power and latency testing measures energy efficiency on neuromorphic hardware with KPIs of power consumption and latency. Thank you. Please visit the VIAVI booth at MWC 26.